Good afternoon, folks. Happy Thursday. I was just battling with GeoGebra, so I'm hoping to be able to show you something, but I am not at all confident that it will work. Anyway. Okay. Today is the 22nd. Okay, welcome. Anyone have any questions? I'm just trying to get all my stuff together. That's not all my stuff. Get that. Well, I hope you had a good couple days. I want to start by saying we'll have a quiz next week. Okay, so let me go ahead and write that down. And we actually, I was supposed to have a quiz this weekend, or I was looking on the schedule, and that's what I had planned. Since I forgot about it, we might have a quiz next week and then also the week after. So we'll just have to see how things go. Okay, so let me just write that down. Quiz next Thursday. And the date will be, or the sections will be 5.1 through 5.3. Okay. The what we were talking about last time. So last time, we were talking about given a basis for Rn, be a basis for Rn, and T, a linear transformation, mapping Rn to Rn. We defined the B matrix for T to be this T sub B, and that to be the matrix whose columns are the images of the B vectors, the basis vectors, but in the B coordinates. So you take the images of the basis vectors, but then you put them in B coordinates. Okay. So, and we saw that if T of X is A times X, and B is a basis, then one more thing, sorry. And B is the basis. Actually, let me be more specific. Let B be the basis consisting of vectors B1 through Bn is a basis. And P is the matrix whose columns are the basis vectors. So if we get all that, then we finally get the then the B matrix of A is P inverse AP. Okay, so let me just real quick do another example. Find a basis B for R2 such that the B basis is diagonalizable, is diagonal if T of X is equal to the matrix. I just want to do one more example. The matrix 2, -5, -1/2. Oh boy, you'd think I'd be able to write clearly, but no, -1 and 2.5. Okay. So I don't know if you remember or not, but last time when we were doing this type of stuff, we were going to use this calculation to say, hey, if this thing is diagonal, then P is just a matrix whose columns are eigenvectors of A, right? Oh, sorry, that's equal to that. So this is my matrix A. So if P equals the matrix whose columns eigenvectors for A, independent eigenvectors. Excuse me, independent eigenvectors for A. If P is that matrix, then 5,3 shows that P inverse AP is equal to a diagonal matrix where D is diagonal. And in fact, the eigenvalues are so what am I trying to say? And the eigenvalues of A are the diagonal entries of D. Okay, so that's what we want to find because we now know. So the previous statement was that the B matrix for T really is just that. So since the B matrix for T is equal to P inverse AP, the columns of P have to be the eigenvectors, and that's exactly the basis that we're looking for. So this problem says find a basis for R2 so that this matrix is diagonal. We know in order to diagonalize A, the columns of P have to be eigenvectors. And this matrix will be my B matrix. So we need B to equal to a basis of eigenvectors. So we can show, I'm not going to go through the whole calculation again, but we can show that for this A, your eigenvalues are going to be 3/2 and 3. And your eigenvectors corresponding to that, to each of your eigenvalues. For 3/2, an eigenvector is 1, 1. And for 3, an eigenvector is -1, 2. And I want to show how to visualize T. So I want to show how this helps visualize T. Just by looking at the image of the unit square. Okay. So if I apply T to the unit, actually, I'm going to draw both pictures in the same coordinate. Okay, so if I just take the regular unit square, which is 1 unit in each direction, and let me remind you what T is. T of X is given by this matrix 2, -1/2, -1, 2.5. X. And I want to look at what it does, what the image of this unit square is. So the unit square is everything in here. Okay. Okay, so now I take this first vector E1, this side, and I find its image. So if I have this E1, what does multiplying a matrix by E1 always give me?
The x-axis of the transformation.
The first column, right? If I take this matrix times 1, 0, I just get the first column of this matrix. Yeah, which would be where the x-axis goes, which is to 2, -1. Right? So that's going to go down here. That's the image of E1. And what's the image of E2? Well, it's the second column, right? Because if I hit cancel, we don't want to. Because if I hit this matrix with 0, 1, that just picks out the second column, which is going to be -1/2, 2.5. And one thing about linear transformations is they take parallel lines to parallel lines. So since, wait, this is what I want. Since the bottom and top of the square are parallel, the bottom and top of the image have to be parallel as well. So this top vector has to be like that, and the one on the other side has to be parallel to the left-hand side, and it has to look like that. So this is the image of the unit square. And T takes this to that, right? Takes red to blue. And that's not very informative necessarily. This is the image of the standard unit square. Not so enlightening. however, we know that, oh, actually, I didn't finish this example. Let me just finish this example by saying that if I let P be the matrix whose first vector is -1, 2, and second vector is 1, 1, then TB is going to be the matrix, the diagonal matrix 3, 1/2, 3 halves, my bad. So we have two ways of looking at our linear transformation. One is the original matrix, and the other is the matrix with respect to the B basis. So with respect to the B basis, I can look at the image of the standard B unit, not the standard unit square, but the B unit square. And I'm going to put square in parentheses. So instead of viewing that, I want to know the image of the B unit square. Okay, and now remember what B was. The B basis is the way I've written it. The first vector is -1, 2. Okay, so this is, oops, -1, 2. And the second vector was 1, 1. So if I go to -1, 2, which is right here, and then I go to 1, 1, which is right there, then I get this parallelogram is what it is. It's not a square anymore, and that's why I've put square in parentheses or in quotes. Okay, so that's what that looks like. Oops. And now I want to know what its image is. The advantage to looking at the B unit square is we know what the transformation does to -1, 2. -1, 2 was an eigenvector with eigenvalue 3. So that just stretches it 3 units. So it's exactly the same direction. It's just 3 times as long. Same with 1, 1. 1, 1 we found was an eigenvector with eigenvalue 3 halves. So applying T just stretches 1, 1 by 1.5. So I go out one of them and then half of one, and that's it. And then the entire square just has to map to a parallelogram. So it has to map to this guy here. So the whole point sort of visually or geometrically, the whole point of changing the basis from the standard basis, which gives us a kind of skewed up matrix, to one like this, is if you change your unit square from the standard unit square to the B unit square, which is not really a square at all, right? It's a parallelogram. If you change it to the B unit square, then it's easy to see the action of this linear transformation relative to that parallelogram. It stretches along both sides. On the one side, it stretches by a factor of 3. On the other side, it stretches by a factor of 3/2. So this is much more enlightening. So much more aesthetically pleasing. It just seems to add a little bit more structure to what your transformation is doing. Okay, so it's the same transformation for both pictures. Both pictures are the same transformation. I'm just saying, what does it do to different shapes? If I look at the standard unit square, it kind of does weird, goofy things, like it kind of stretches it out and moves it like that. And it's just hard to describe what it does. When you use the B unit square, it's easy to describe. It stretches by a factor of 3/2 on one side and 3 on the other. Any questions about that? So this is an algebraic way. This whole part of the example is algebraically, how do you diagonalize the matrix for a linear transformation, or find a basis that diagonalizes it, right? And the fact that it's diagonal actually has geometric consequences, right? If you work with this basis, then the transformation is easier to visualize than it is working with a standard basis. So this is the geometric aspect. The previous page was the algebraic aspect. And I'm going to hope that my GeoGebra still is working. Let's see. Yes, so here we go. So here, it's exactly what we just drew, but I thought it'd be useful to have it, for you to have it written in your notes. But this is just the same linear transformation with the unit square mapped to that parallelogram that's a little bit off, okay? And in this basis, it's hard to visualize what's going on with this transformation. And if I get rid of those two, and I look at the B unit square, which is no longer a square, right? Undo that. What just happened? Undo that. Okay, so I need this to go down. If I look at the B unit square, its image is just 3 times in this direction and 1.5 times in that direction. And that's exactly the picture you have. Okay. Not that this is any more rigorous than the picture I drew, but this is hopefully just a little bit more maybe convincing that the picture really is nice. They're nicer parallelograms, right? I couldn't draw such a nice parallelogram as this. Okay. All right, so I'd like to do one more example from this section, section 5.4. And it's, so that example was sort of calculating, how do you calculate it so that your matrix is diagonal? With what basis gives you a diagonal matrix? Together with geometrically, what makes sense in terms of, or why is that desirable? Why do I even want to make it diagonal? And the idea is you get a better picture. There's also, if you look at the homework from 5.4, there's also going to be a couple of sort of matrix algebra type questions. So I just want to do a matrix algebra question similar to the homework. So here, if B is equal to P inverse AP, and X is an eigenvector of A with eigenvalue lambda. So A is the matrix in the middle. So A and B are similar matrices, right? They're similar matrices. And we know an eigenvector and corresponding eigenvalue of A. Turns out that that allows us to find an eigenvector of B. Okay, so then P inverse of X is an eigenvector of B with eigenvalue lambda, or show, actually, that's what I should write. Not then, but show. And this is a matrix algebra question. What I mean by that is it's not necessarily calculating exact numbers like we've been doing. Rather, it's just working with matrix algebra. And so what I'd like to write down is my givens and my goals algebraically. Okay. So one, I'm told that B is equal to P inverse AP. So I'm given that B is P inverse AP. And I'm also given that X is an eigenvector of A with eigenvalue lambda. Now, that's a lot of words, okay? Eigenvector and eigenvalue and all that stuff, but there's a very clean algebraic way of writing that down. So if I say X is an eigenvector of A with eigenvalue lambda, the equation that you get is, that means if you multiply X by A, you just get lambda X. That is exactly what it means. That's a definition of an eigenvector. So rather than leaving it in English like it is here, X is an eigenvector of A with eigenvalue lambda, I'm going to write it as, that means AX is lambda X. That's what it means. And our goal also has a nice algebraic way of writing it down, right? Our goal is to show that P inverse X is an eigenvector of B with eigenvalue lambda. So what algebraic equation do I have here that's equivalent to this, that shows you that P inverse X is an eigenvector of B with the same eigenvalue? What should I write down right here? I'm going to take this moment while you're thinking about that to blow my nose. My allergies are just killing me. Okay, so now I'm done blowing my nose. You can feel free to tell me the answer. What algebraic equation do I get to write down? This is an eigenvector of B, right? So what does that mean? If I multiply this vector, P inverse X times B, what should I get? Well, let's look at this example. for me to say that X is an eigenvector of A means that if I multiply X by A, I just get lambda times X. So if I say that P inverse X is an eigenvector of B, that means I know what happens if I multiply P inverse X times B. I just get lambda times it. And that's what we have to show. So I took this English and I just turned it into algebra. Okay, so if I want to show this, I'm going to start with the left-hand side and just start calculating. All right, we'll start with the left, the B times P inverse X, and we'll just start calculating and hope we can figure out why it's lambda times P inverse X. So I got B times P inverse X. Going to do a bunch of stuff, right? So I'll do a bunch of junk until I get down here, and I'm going to want this to equal lambda times P inverse X. Okay, and if I want to start doing some calculations, right, I really don't know what B times P inverse X is. So I don't know how to simplify this offhand. It's not like I can look at that and say, oh, I know how to do this, right? So if I'm wondering what to do, I'm going to go back to what's given. And I'm going to ask myself, is there anything in the given that will help me figure out what this is? Is there any way you can see either of these two givens, right? So this is like my given 1, and this is like my given 2, right? Given 1 is B is P inverse AP. Given 2 is AX is lambda X. Is there any way that either of those could help you start calculating this product?
Could you set the right side of the first equation multiplied by P inverse X equal to that?
Yeah, so another way to say that is just substitute for B, right? So I know that wherever I see a B, it's the same as P inverse AP. So I'm just going to substitute that in. So that's P inverse AP times P inverse X, right? And this was given 1, right? That's why I can do that. I'm hoping you're now smiling a little bit, right? Because you can see like the next thing, what's the very next thing you want to do in this mess? Well, go ahead.
Multiply together the P and the P inverse.
Yeah, because those just cancel, right? It's like multiplying by 3 and then multiplying by 1/3. They just cancel. So these two just cancel. So this just gives me P inverse AX. And this is like the associative property, if you want, and the fact that P times P inverse is the identity, right? Which plays the role of 1. That's why it just completely disappears. Okay, but now Now we have P inverse AX. And I want to get to lambda times P inverse of X. Still got my P inverse, that's nice. But I don't have just X, I got A times X.
You substitute a times x with lambda times x.
Yeah, so you just use the second given, which just says AX is lambda X, where lambda is a scalar now, right? Whereas A was a matrix. So this is P inverse of lambda X, right? And this is, the reason for that is given number 2. But then the last thing you know is that if you have a scalar, you can pull it out. So scalars pull out. And that's not precise of matrix multiplication. And we're done. Right? So the reason that this second to last row is equal to the last row is I just take the lambda and I pull it past the P inverse. Okay. That's it. So if you look at the homework from 5-4, there's a variety of things. There's some calculations like we started out with today where you had to diagonalize things or maybe just find the matrix, the B matrix. But there's also a couple of more word problems or show problems where you got to do sort of matrix algebra to get from one expression to another or something like that. Any questions about that? Okay. All right, so I'd like to start talking about 5-5. 5-5 is complex eigenvalues. Okay. And eigenvectors, or just, yeah, what happens if you have a complex eigenvalue? Okay. And these are needed, so you run into them because suppose I had A is the matrix, the 2x2 matrix with zeros down the diagonal, 1 in the lower left and -1 in the upper right. Suppose I want to find the eigenvalues of this matrix. So I got to solve. In order to find it, I solve the determinant of A minus lambda I equals 0. And that determinant just subtracts lambda from the diagonal entries, right? And if you take that determinant, you get lambda squared plus 1. And this has, so lambda squared is -1 and lambda is plus or minus I, right? So complex values of complex eigenvalues do arise in very natural settings. And I've been told, I do not know, but if you're a physics major, this is important. Okay. And even if you're a math major, complex eigenvalues come up in differential equations. Okay. So we're going to have to deal with them. All right. Any way you look at it. In order to do that, I think, so I have this, I'm really into complex numbers now. I think I never liked them when I was in graduate school. I never liked them when I was in in not for until like 5 years ago, I started reading a book called Visual Complex Analysis. And all of a sudden, complex numbers seem to have a much richer structure than the real numbers. And it's just got a lot more going on. And everyone and their brother needs to hear about it. Okay, so I'm going to take this opportunity to talk to you guys about the geometry of complex numbers. And even in this class, I think you're going to be surprised at how relevant they can be and how easy they make things and how much more meat there is compared to the real numbers. So I'm going to spend a while just talking about how cool complex numbers are. Okay, so here we go. So let's talk about complex numbers. So way better than real numbers. Anyway, that's a joke. Okay, so some other you talk to another prof, they'll probably scoff at me for saying this, but this is my current attitude. Okay, and if I'm going to talk about complex numbers, there's sort of two ways I want to talk about them. One is algebraically, and that's the way that's the way I learned them. Okay, I learned them algebraically, and like the beauty of complex numbers was hidden because nobody ever told me. So I'm going to tell you about the beauty. So algebraically, you add a new number or you adjoin. It's a technical math term. Anyway, you adjoin a new number, and that new number is I, which is the square root of -1. Okay. By the way, if it's the square root of -1, then I know what is I squared.
-1.
Yeah, it's -1, right? That's what I mean by a square root. So this is the number. So if I multiply it by itself, I get -1. Okay, so we're going to join this number to R, to the real numbers. And to the real numbers to get complex numbers. So, and algebraically, this is very straightforward. I'm sure that you guys have seen this a couple times, even if you haven't really thought about complex numbers a lot. So it's just like A plus BI, right? That's what it is. If Z is in C, Z is a complex number, means that Z equals A plus BI for some real numbers A and B. So for some A and B in the real numbers. And this is, I'm not saying anything new. None of this is new. But you may not have ever thought about it. Anyway, so some examples, 2 minus 3i is a complex number. Pi plus 7i is a complex number. Actually, the square root of 7i is a complex number. In fact, -4 is a complex number. So are all complex numbers. What does it mean to be a complex number? It means that I can find an A and a B such that that number is equal to A plus B times I. Okay, that's what it means. So what about this -4? How is that a complex number? -4 is in the complex numbers because -4 is equal to -4 plus 0 times I. To show that a number is, actually I should say this, to show that a number is a complex number, I have to be able to write it as a real number plus another real number times I. Well, you're allowed to use 0 as one of your real numbers, okay? So that's why the real numbers are actually also a subset of the complex numbers. Okay, and now we're going to talk about arithmetic. So that's what a complex number is. I have to be able to write it as a plus bi. I want to talk about arithmetic with complex numbers. Oh, no, sorry. I don't want to do that yet. One other thing. Oh, come on, get big. Why is that so small? It says it's as big as it can get. Okay, I want to do one other thing. I want to define some terminology and notation. Okay, so if z is a complex number, then I know z is equal to a plus bi, okay? The real part of z, I want to tell you what that means, okay? A lot of times we'll denote it by just capital R, and then small e of z. So the real part of z, that's just equal to a, right? That's just the real number part of it, right? It makes sense. The imaginary part of z, we'll denote it by capital I m of z for imaginary of z. Turns out that that's just b. And I thought this was strange, okay, because b is a real number. Actually, I forgot. Let me remind myself. Google imaginary of z. It just seems strange to me that the imaginary part would be a real number. Like I would have expected maybe b times I. I looked it up once ages ago and found that that's what it was. And I'm going to have to go convince myself again that it really is. But for now, let's just call the imaginary part of z to be the coefficient of I. Okay. And the coefficient of I is really a real number. Okay. And then one other thing that happens frequently in complex numbers is just complex conjugation. So the complex conjugate of z, it's denoted by z bar, z with just a bar across the top. And it's just what you get. And you probably have seen this. It's just, and maybe not. It doesn't matter if you have or not. It's just what you get if you negate, if you change the sign of the imaginary part. Okay. So for example, the imaginary part of pi plus 7i is 7, right? Until I Google it and make sure that I'm right, I got to do that, right? The imaginary part of -4 is 0. if I take 2 minus 3i and I take its conjugate, that's just what I get if I change the sign of the imaginary part. So I turn it into 2 plus 3i instead. Okay. Just getting used, I guess I should do a real part, right? So the real part of pi plus 7i is just pi. Oops, I needed an RE in there. And the real part of square root of 7i is 0 because there's no, that's a purely imaginary number. So this is sometimes called a purely imaginary. Okay. So I'd like to talk about arithmetic with complex numbers. So this, again, this is, hopefully you've seen this before, but it doesn't matter if you have or haven't, but so arithmetic with complex numbers. And by arithmetic, I mean addition, subtraction, multiplication, and division. That's what I mean. You give me two complex numbers, I should be able to add them. I should be able to subtract them. I should be able to multiply them. I should be able to divide them. Okay. And when I add two complex numbers, I should get another complex number. When I divide two complex numbers, I should get another complex number, and so on. So arithmetic with complex numbers, the overarching thing to remember is you do arithmetic thinking of I as a variable, and then remembering that I squared is -1. Okay, so do normal arithmetic with I as a variable. So you treat it just like you would an X, right? So in your mind anyway, if you see 2 minus 3i, you think 2 minus 3x, okay? So you do normal arithmetic with I as a variable, and then you remember that I squared is -1. Okay, and this is, yeah, let's just highlight this. How come this is now blue? That's how you do arithmetic with complex numbers. So let's do a couple of examples. So if I want to talk about addition, if I want to take 2 minus 3i plus 3 plus 2i, I just combine like terms, okay? Like if this was 2 minus 3x plus 3 plus 2x, you would know what to do. This is not a mystery to you. You know how to handle it. So you do the same thing with i's, okay? So that you say that, well, I'm going to look at the 2 plus 3, right? And then I'm going to look at the minus 3i plus 2i and combine like terms. So this is going to give me 5 minus I. So basically, I'm just combining like terms. Okay. That's with complex addition. Complex multiplication. 2 minus 3i times 2 plus 3, or 3 plus 2i. Again, you do normal arithmetic, okay? So like if it was 2 minus 3x times 3 plus 2x, you would FOIL it out. And that's exactly what you do. So you get your 2 times your 3. That's the F from FOIL. Then the outers is going to be 2 times 2i, right? That's the O from FOIL. The inners is going to be negative 3 times 3i. That's the I from FOIL. And lastly, I'm going to get negative 3i, sorry, shoot. So if it was negative 3x times 2x, you would just get negative 6x, right? Squared. But it's going to be negative 6i squared, and that's the L. So you FOIL it out normally. So the difference when you're multiplying them from when you're adding them, when you're adding them, you never get like an I squared, right? So you never have to do the remember I squared is -1, okay? Don't have to do it. Here, when you multiply them, you do get an I squared. So you do have to figure that out. So this is going to be 6 plus 4i minus 9i. And now I squared is -1. So instead of minus 6i squared, I just get plus 6. And then I combine like terms. So to get from there, so here I use the fact that I squared was -1, right? And now I combine like terms and I get 12 minus 5i. Any questions about that? Okay, division is a little trickier. Okay, so I got to show that something like 1 plus I divided by 3 plus 4i is a complex number. Okay. And to show that anything is a complex number, I have to show that it's of this form. Any complex number has to have a real part plus a purely imaginary part. Okay, so I have to be able to take this quotient and rewrite it as, I got to show that this equals a plus bi for some a and b in the real numbers. Okay. And the trick is to multiply top and bottom by the conjugate of the denominator. Multiply by 3 minus 4i divided by 3 minus 4i. So we're going to assume that any number, even complex numbers, any number divided by itself is 1. Okay. So I get 1 plus I over 3 plus 4i times 3 minus 4i over 3 minus 4i is equal to. Now, in the bottom, you're going to FOIL it out and you'll get 9. And then the outers gives you minus 12i. The inners gives you plus 12i. And the lasts gives me minus 16i squared. And the top the first gives me 3, the outers minus 4i, the inners plus 3i, and the lasts minus 4i squareds. So now if I notice the terms with the i's in it disappear, right? This is like a difference of squares right here. This is like a plus b times a minus b. And that's going to be a squared minus b squared. The only thing here is you've got the complex number I. So now we have to remember that I squared is minus 1. So this actually isn't minus 16 anymore. It's really plus 16 once we make that simplification, right? So in the denominator, I'm just going to get 9 plus 16. In the numerator, this minus 4i squared is really going to be plus 4. Right? Because that's plus 4. So the 4 and the 3 give me 7. And then I get minus 4 plus 3i. So that just minus 4i plus 3i. So that just gives me minus I. Okay, so this gives me 7 minus I over 25. And just like in real numbers, this is 7/25 minus 1/25 I, right? You can take a fraction and you can split it, because as long as the way you add fractions is to have a common denominator. So I can just add these straight across to get that back. Okay. So to show that the quotient of two complex numbers is again a complex number, you just multiply by the conjugate of the denominator, top and bottom. Anytime you multiply a complex number by its conjugate, you're going to get a real number because the middle guys always cancel. And it's really just going to be this, it'll be like a squared plus b squared. Anyway, and that real number then allows you to split up your division and figure out what it is in the form a plus bi. Okay. Any questions about that? That is algebra with complex numbers. Okay, folks. Arithmetic with complex numbers from an algebraic standpoint. So I'm just going to say that complex numbers are ones that look like this. And I'm going to say if I want to do arithmetic, I do it algebraically as if I were a variable. And every time I see an I squared, I turn it into minus 1. Actually, let me do one more example. Suppose I had 1 plus I cubed. That's going to be 1 cubed plus 3 times 1 squared times I plus 3 times 1 times I squared plus I cubed. So I don't know if you know the binomial theorem, but you can multiply these things out really easily. And so I can now simplify this. This becomes 1 cubed is just 1 plus 3i, right? But now this I squared is just minus 1. So this becomes minus 3, right? But now this I cubed is really I squared times I, right? And I squared is minus 1. So I just get minus I when I do this. So this is equal to minus I. So the point is, because I squared is -1, even if you get higher powers of I, you can always pull out a bunch of squares and you can always reduce it to where the I is just raised to the first power. Okay. And now you can simplify this product, right? So it's going to be -2 plus 2I. Okay, so that's my last example of that. Any questions about the just arithmetic with complex numbers? Okay, let's take a 5-minute break. Welcome back. Anyone have any questions about complex numbers before we get started again? Has everybody seen them before? Thumbs up, yes. Clapping, no. It doesn't matter if you have or not. I'm just wondering, like, one person, yes. Yeah. Okay, good. Well, this might be some review, but we're going to talk about some geometry of them, which probably maybe not a review, but in any case, it doesn't hurt to review. So I want to talk about the geometry of complex numbers. And it really, actually, historically, complex numbers had an interesting beginning. They came up when people were studying solutions to cubic equations. They couldn't get around complex numbers, not quadratic equations, but cubic equations. And so complex numbers had to take on a meaning, but people did not want to. That's why they call them imaginary numbers, because people didn't believe that they were real. Okay, that's why they call real numbers real number. That's really the reason. And mathematicians didn't want to accept them. They had no idea what the square root of, a negative number could be. And it wasn't until they achieved a geometric interpretation that people started to accept them, because they were more comfortable with geometry, even though they arose in a purely algebraic setting to begin with. And so that's what I want to talk about now is the geometry and complex numbers and vectors. Complex numbers are vectors. Okay, this is the big R, vectors. This is the big, that's how you want to interpret it. That's where they started to catch on when people, I mean, it's hard to believe that no one realized that complex numbers could be represented by vectors to begin with, but that's just because we're always taught that they are, right? So the idea is if you can map complex numbers to R2 and back, right? You can just take any complex number Z, which is A plus BI, and you can turn that into the vector AB, right, in R2. Okay, and we can talk about complex addition. So in this correspondence, notice that if I have, so note that complex addition corresponds to vector addition. Okay, and what I mean by that is, suppose you got two complex numbers, Z and W, and Z equals A plus BI, W in its real and imaginary parts is C plus DI. Okay, then I can look at in C. So I'm going to do everything in C down here and in R2 down here. And we're going to think of this correspondence between the two. Okay, so C is, so if sorry, let me erase this. Z plus W is going to be A plus BI plus C plus DI, right? And I can find the corresponding vectors separately. So the vector Z plus the vector W is going to equal the vector AB plus the vector CD, right? But now this equals, let me change the color. This equals A plus C plus B plus DI, just by combining like terms, right? And if I do the vector addition down here, you know that you add entry-wise. So you get A plus C, B plus D. And what you notice is that if I take this sum and I find its corresponding vector in R2, I get exactly the sum of the vectors that correspond to the original complex numbers. Okay, so complex addition corresponds to, so I have a nice visual for complex addition. So my visualization for, so we can visualize complex numbers, first of all, complex numbers as vectors. And complex addition as vector addition. So normal tip to tail, right? Type stuff. So let me just do an example. If I wanted to visualize, so 2 plus 3i, again, this is probably something you're familiar with. If z equals 2 plus 3i, I can visualize that in R2 as the vector that goes 2 units horizontally and 3 units vertically. And so that's my complex number z, right? That's how I can visualize it. And if I wanted to add 2 vectors, so if I wanted to, if I have W equaling minus 1 plus 2i, then I could sketch W in there. That's my other complex number. And I can sketch Z plus W just by doing the normal tip to tail, right? And so the vector from the origin to the tail of Z to the tip of W, that is the complex number Z plus W. Okay, so I can have example sketch. This even works for several vectors. Even works for several vectors. So for example, suppose I have 5, 2 plus 3i, and 4i. These are all complex numbers. I want to sketch their sum. 5 plus 2 plus 3i plus 4i. Okay. Okay, so pop quiz. What kind of vector is 5? If I want to think of 5 as a vector. I'm thinking of 5 as a complex number. Every complex number can be represented as a vector in the plane. What vector is 5? The 2 plus 3i we're already good with, right? The 2 plus 3i we're already good. Oh my goodness, what just happened?
Would it probably be 5, 0?
Yeah. Yep. The imaginary part just tells you the y coordinate, right? So if I wanted to sketch these, let me use colors. So, all right. So 5 is just the vector that goes out 5 units, right? So this goes 1, 2, 3, 4, 5 units. And then 2 plus 3i we already did, right? So let me go 1, 2, 3, 4, and just for fun, 5, 6, 7. So the real numbers correspond to horizontal vectors, right? Just vectors on the x-axis. 2 plus 3i, let's remember where we were with that. That's just this vector, right? So that's z. Well, okay, I'm not even going to write it. This is 2 plus 3i, right? And then what about the 4i? What can you tell me about that vector? What
0,
about
4?
Yeah, that's got 0 for your on your real axis. This is the imaginary axis. That's the real axis. So 4i is just the vector that goes like that. Right. Okay. So if I want to sketch the sum, I can just take tip to tail. So first I lay down 5, then I lay down 2 plus 3i. Right? So that's going to go to the right 2 and up 3. And then I want to add 4. So I've got from 3, I go up to 4, 5, 6, 7, right? So I got my 4i. And their sum, which will be yellow, is from the origin all the way out to the tip, right? So this is the sum of, oh my goodness, let me undo it. This is the yellow sum, right? That vector, if I just add multiple complex numbers, I can just do them tip to tail like that. So this is the 5 plus 2 plus 3i plus 4i. And if we get around to it, there's really cool applications because you can talk about infinite series of complex numbers, and you can see that they converge when these vectors sort of spiral around a specific value that it converges to. So, so really cool stuff with some cool math. All right. So you can visualize complex numbers. They're just vectors. But you can also notice that complex addition is just the same as vector addition. So you have a nice geometric way to understand complex addition. All right. Okay, I want to talk about a couple of other common terms and notations and quantities associated with complex numbers. So other quantities associated with complex numbers. And it really stems from thinking of them as vectors, okay? It really does. So I'm going to think of this complex number z equaling a plus bi, right? I can think of that as a vector. So I'm going to do that right here. This is my a plus bi. And what you notice is, that's my z, sorry, that z. What you notice is a vector has a length and a direction, right? And there's a little right triangle in here. I wonder if I can just make this thinner or something. Let's just make it thinner. There's a little right triangle in here. Why is that so thick? And this has length B and that has length A. And like in terms of a direction, a lot of times we'll talk about the angle a vector makes with the positive x-axis. And a lot of times we'll talk about the length of the vector, okay? So I'm going to go back to this guy. All right. So the modulus, still a little thin, sorry. What happened? The modulus of z is the length of z thought of as a vector. So it's denoted by the length of z, or, you know, absolute values finds around z. And this is just the square root of a squared plus b squared. And it comes from the Pythagorean theorem, right? It's just the length. That's the modulus of z. And then the argument of z it's denoted by arg of z, and it's equal to the angle with the positive x-axis. Okay, and that's probably good enough, but I will, so in our notation, that's theta. I will mention that this is the arctangent of b over a, opposite over adjacent, right? This is the arctangent of b over a. Whenever a is positive, if a is negative, it's pi plus the arctangent of that b over a. It's really, that's probably not as important as you remembering that the argument is the angle it makes with the positive x-axis. Okay. So those are two other quantities associated with yeah, okay. Geometrically. Associated with complex numbers that come from geometry. Okay. Let's also look at complex conjugations geometrically. So we got modulus, we got argument. Complex conjugation. I'm going to do that later. I'm going to talk about that later. I want to talk about complex multiplication. And actually, before that, I might even talk about Euler's formula. So this is a big deal. Euler's formula. Says that e to the I theta is equal to cosine theta plus sine theta times I. There are several ways to convince you that this should be the right definition. All of them involve like more math than you guys probably know. One is to involve Taylor series. You just relate the Taylor series. Another is to take derivatives of complex functions. Anyway, I'm not going to mess with it. We're just going to take this as fact. Okay. We're just going to say, hey, let's look at some of the consequences of this formula. So observe that e to the I theta is a unit vector. Okay, so let's just take a look at this, right? Cos theta, if I go out to the point that's at cos theta sine theta, if this is my angle theta and I'm a point on the unit circle, you know that this is going to be the coordinates of that point are cosine theta sine theta, right? That's just from the unit circle nonsense. So this really is cosine theta plus I sine theta, right? Because sine theta times I. So cosine theta is just the real part, so it's a horizontal vector. Sine theta I is a purely imaginary number, so that's a vertical vector. And if you go cos theta and up sine theta, you get to e to the I theta. That's what Euler's formula says. So they're always unit vectors. Okay. And you can talk about the polar form of a complex number this way. Okay. So the polar form of a complex number. So we have the Cartesian form. The polar form just involves the polar coordinates. So all you got to do is e to the I, if you start with a complex number, which is a vector, okay, so I start with z, I know that there's a unit vector in that direction. And if the length of z is equal to r, then the argument of z is just equal to some theta, and e to the I theta is the unit vector in that direction. So z is equal to r e to the I theta. And that's the polar form of a complex number, where theta is the argument of z and r is the modulus of z. Okay, so let me just do an example. Find the polar form of 2 plus 2i. So I need to sketch it first, right? So 2 plus 2i goes from the origin to the point 2, 2. So I know I just need to find the modulus of 2 plus 2i, and the argument of 2 plus 2i. And this really is just finding the polar coordinates of the point 2, 2, right? The endpoint of this guy is 2, 2. And I just want to know what's the argument, theta, and what's the modulus, which is r from polar coordinates. That's what I wanted to do. Oops. So does anyone remember what what's the argument of 2, 2? What's the angle that this line makes with the positive x-axis?
45 degrees.
45. So I'm going to use, I'm going to always use radians. So I'll say pi over 4. And the length of that vector, you just use the Pythagorean theorem, right? It's this squared plus this squared, and then you take the square root. So this is the square root of 4 plus 4, which is 2 root 2. So the polar form of this guy is 2 root 2 e to the I pi over 4. That's a 4. It doesn't look like a 4. So we have these two ways of writing complex numbers. One is in polar form and the other is Cartesian. And you should be able to go back and forth, find the Cartesian form of, say, 3e to the I pi. Now, eventually this will be, you'll get used to it. For now, this is the first time you've seen it maybe. So we're going to just say that e to the I pi is cosine pi plus sine pi times I. So this is just going to be 3 times, actually, before we, oh my goodness, come on, Rob. Okay. Before we do that, let's even sketch this. So if I sketch this, I go out 3 units on an array that makes an angle pi with the positive x-axis. Okay. So I go through an angle of pi, which is the same as 180, right? So I go through an angle pi, and then I go out 3 units. Okay, so, and that's my z. If this is z, that's my vector z. So in polar forms, it's very easy to sketch. You just go to the right angle and go out the right distance, and you're done. Okay. Well, I'm going to use, and so hopefully you realize that this has to be a real number, and it's got to be 3 units to the left of the origin. So it better be -3, right? When all is said and done. And in order to see it, we're just going to plug it into Euler's formula, the exponential. So this is the cosine of pi plus the sine of pi times I. But the cosine of pi is -1. The sine of pi is 0. So this is -3. Okay. you should also see that the unit vector just means length 1. E to the I pi is just -1. That's also called Euler's formula. It was like a big, it's got, the reason it's significant is it's got pi, it's got E, and it's got -1, like 3 big numbers, whatever, relating them. So we have 2 ways to describe complex numbers: their Cartesian form and their polar form, right? So I can go from Cartesian to polar, just getting polar coordinates. I can go from polar to Cartesian, just getting Cartesian coordinates from polar form. So the Cartesian form of complex numbers is the right way for the Cartesian form of complex numbers helps visualize complex addition. The polar form helps visualize complex multiplication. Okay. So suppose Z is given by R e to the I theta, and W is given by S e to the I phi. Now R and S are real numbers here because they are just how long the vectors are. So the e to the I theta is a unit vector, so it's only length 1. And then you multiply it by R, so that just stretches it so that it's length R, right? Then Z times W is equal to R e to the I theta times S e to the I phi. And here is the absolute miracle of miracles, that all of your algebra and arithmetic with exponents still works in this much more general context. So this just becomes RS times E. And what do you do with exponents? If I have e to the I theta times, maybe I should just write it out, times e to the I theta times e to the I phi. So what do you do with exponents when you multiply something with the same base?
You add them.
You add
I
them.
think so.
Yeah, so this is going to be RS, and then I can factor the I out, and I get e to the I theta plus phi. Okay. Now this is huge because it tells you what multiplying does geometrically. Notice that the length of the product is just R times S, right? In the polar form, the coefficient of E is the length. So the length of the product is the product of the lengths. So observe that the modulus of Z times W is just the modulus of Z times the modulus of W. Because this is RS and this is R times S. Right. But what about the arguments? The argument of ZW is the angle. And the angle, remember, the angle is just the coefficient of I in the exponent. So here the angle was pi over 4, so that's up there. Here the angle is pi, so that's up there. So the argument of Z plus W is theta plus phi. So that's equal to the argument of Z plus the argument of W. So to multiply two complex numbers, you add the arguments and you multiply the lengths. So to multiply Z times W, you add arguments and multiply lengths. So I want to talk about complex arithmetic and transformations of the plane. So complex, and let me just start with complex multiplication. And transformations. Of the plane. And I'm going to start with a very elementary example. Pop quiz. Sketch the complex number I. So this is just a complex number, so it's in C, and I want to sketch it. Where is its endpoint? So I know that it's going to start at the origin. Where is its endpoint? Thinking of this as R2, like points in the plane. Where should I draw this vector I? Well, I have to think of this as some A plus B times I, right? So what's A in this case?
0.
0. And what's B? 1. Yes, you're right. So it goes to the point 0, 1. So I is the unit vector, the vector that's 1 unit long and goes straight up. Okay. So that's what I is. So what is the length of I? Sorry, my bad. The length of I? Not a trick question.
1.
That's just 1. And what's the argument of I?
Pi over 2.
Pi over 2. And that's because this angle here is pi over 2, right? It's a right angle. Okay, so we know a lot about I. So suppose I wanted to now sketch I times 1 plus I. Oh, actually, so before that, what's even 1 plus I? Everyone should be able to sketch 1 plus I. So here's 1 plus I, right? It goes to the right 1 and up 1. The real part just tells you how far to go horizontally. The imaginary part tells you how far to go vertically, right? So we know that multiplying numbers adds arguments and multiplies length. So multiplying 1 plus I by I adds pi over 2 to the argument of 1 plus I and multiplies the length by 1. Right? In other words, it leaves it the same length. So maybe I should say that, right? Because multiplying the length by 1 just says it leaves it the same length. So I times it, I know, just leaves it the same length, but adds pi over 2 to it, right? Those are supposed to be the same length. So this will be I times 1 plus I. Well, what would it do to this vector z? If that's z, it's still going to add pi over 2 to the argument. So that just means I go pi over 2 more, and it's still going to leave it the same length. So this is going to be I times z. And you know that you've added pi over 2 to the argument. So that what that tells me is I have a transformation from C to C where I take any vector z and I transform it to I times z. What is that transformation? How can you describe what it does, given these two examples? Well, it keeps it the same length, but it rotates it by pi over 2. So this is a pi over 2 rotation counterclockwise about the origin. More generally, so let me just say this because I only have 1 minute left. So more generally, fix some a in the complex numbers. I can use a to define a transformation. Then the transformation z goes to a times z is a dilative rotation. The rotation is by the argument of A, and the dilation is by the modulus of A. So in the case that we just looked at in the above example, the modulus of I is just 1. So there was no dilation. You weren't stretching away from the origin. And the argument of I was pi over 2. So since there's no dilation, it's simply a rotation, and you're just rotating by pi over 2. And that's what we found there. When you change this from I to a more general complex number, you could also have some dilation along with the rotation. You'll always rotate by the argument of that A, and you'll always dilate by the modulus of that A. Okay, so I will definitely get some notes out to you about this over the weekend. But what you really need to be studying is 5.1 through 5.4, okay? Especially 5.1 through 5.3, since the quiz next week will be on those sections. Okay, but this is like the tip of the iceberg. We're starting to think of complex multiplication as a transformation in the plane. Okay, any questions? All right. We'll talk to you guys. Have a great weekend. We'll see you guys on Tuesday.